When we encounter quadratic equations in real-life situations, they often have really unpleasant numbers in the coefficients. And this is where the quadratic formula really gets to shine. We don't really want to do a lot of complicated algebraic manipulations with these unpleasant numbers. We just want to throw them into the quadratic formula and just get a result as a decimal approximation. And when we're doing that, the only complication that we need to be really conscious of is that when we're getting a decimal approximation, we don't want to round in the middle of the process. So in particular, we're not going to want to take a square root, round it, and then keep working with that rounded square root. And the reason for that is if we round something and then we divide it by something else, that round off error can explode violently, and we don't want that. So let's see an example that comes from a real life application where we have unpleasant numbers. So in physics, we get quadratics, among other things, when we're talking about throwing something into the air and then it accelerates due to gravity. So we have a thrown ball. T seconds after it's thrown, its height in meters is given by negative 4.9 t squared plus 17.3 t plus 0.8. And we want to use the quadratic formula to determine at what times the ball is 5 meters off the ground. So 5 meters off the ground means h of t equals 5. So negative 4.9 t squared plus 17.3 t plus 0.8 equals 5. That's not in standard form, so we'll start by subtracting 5 on both sides. Negative 4.9 t squared plus 17.3 t minus 4.2 equals 0. For the quadratic formula then, we'll have a equals negative 4.9, b equals 17.3, c equals negative 4.2. And our variable here is t. So the quadratic formula is going to say that t equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So plugging in, t equals negative 17.3 plus or minus the square root of 17.3 squared minus 4 times negative 4.9 times negative 4.2. And that's going to be all over 2 times negative 4.9. Now, we don't want to go too much step by step because we don't want to just copy these ugly numbers over and over again. But we also don't want to just throw this whole thing into our calculator at once because it's really easy to lose track of what we're doing. I find that a happy medium is to work out the discriminant first. So we'll have t equals negative 17.3 plus or minus the square root of 216.97 all over 2 times negative 4.9 is negative 9.8. And now on the calculator, when I enter this, I can either enter it in a way that actually looks like a fraction if my calculator has that feature. Otherwise, I need to make sure I put my numerator in parentheses. So I'll say t is negative 17.3 plus square root of 216.97 all over negative 9.8 is approximately, to 2 decimal places, 0.26, or t equals negative 17.3 minus square root 216.97 all over negative 9.8 is approximately 3.27, rounding to 2 decimal places. And we can check those, right, just by plugging them into the original function. So h of 0.26 is negative 4.9 times 0.26 squared plus 17.3 times 0.26 plus 0.8 works out to exactly 4.96676, which is indeed approximately 5, which was my goal. H of 3.27, that's negative 4.9 times 3.27 squared plus 17.3 times 3.27 plus 0.8, and that works out to exactly 4.97579, which again is approximately 5, which was again our goal. So when we're plugging these ugly numbers in, the most likely source of error is copying the ugly numbers wrong. And the second most likely source of error is rounding that square root in the middle. So avoid rounding the square root in the middle. Copy the numbers very carefully. And these ugly numbers are really the quadratic formula's time to shine.